Hi, my name is Gidi Navon, and I'm a senior principal architect at Marvell Semiconductor. And today I'm going to share with you an AI work we did called Online Feature Extractor and Ensemble of Autoencoders for high-rate anomaly detection in networking. This work was done together with my colleague, Ziv Tomarov. But first, a few words about Marvell. Marvell is a global fabless semiconductor company with over 5,000 employees worldwide. We have over $3 billion in revenues, and we were founded over 25 years ago and have major R&D sites in the US, Israel, India, Germany, Argentina, and China. We are focused on data infrastructure, and we're covering the carrier segment, the devices for 5G base station, the enterprise campus, cloud and enterprise data centers, and automotive. And we have a most complete data infrastructure portfolio, starting from processors, storage, networking, the business unit which I'm part of, and security processors. And some examples of our products: on the compute, we have our Octeon data processing unit coming from our Cavium acquisition. On the networking, we have high-speed transceivers and coherent DSPs from our recent Inphi acquisition. We have CopperPhy, Ethernet switches, NICs, products for cars. And on the storage, we have HDD and SDD controllers and fiber channel cards. Okay, let's start talking about AI in networking. So many AI solutions are currently done in the cloud. But if you want to do AI for networking, this usually means you need to almost duplicate the traffic in order to bring the data to the AI servers. This is not practical and is one of the reasons that AI for networking is not that common. There is a trend to move AI to the edge. We are all familiar with this trend when talking about face recognition in our cell phones, but now we want to do similar things for networking. The challenge with AI for networking is to handle very high bandwidth, high packet per second rate, and in some cases react fast. For example, when you detect an anomaly in the network, that can be a security threat. But what is the motivation of AI in networking? There are several use cases that are being discussed, such as application classification, classifying encrypted flows to their applications by just looking at the traffic patterns, and applying, for example, quality of service parameters to them. AI can help in applying, for example, configuring complex networks, such as optimizing location of Wi-Fi access points, perform traffic predictions for network planning. AI can help identify configuration errors and network faults by analyzing the correlation and correlating huge log events. But today we will share with you our work that is focused on a use case called anomaly detection, which means identifying abnormal traffic patterns that may indicate that something went wrong. For example, identifying malicious flows, an intruder that has penetrated our network, a flow that behaves different than the normal flows in the network. A denial of service attack, a new source sending exceptionally high traffic, faults of devices, a sensor that has stopped sending traffic, content theft, traffic being suddenly sent from a surveillance camera to a new destination, and more. Some background. Neural networks are great in detecting nonlinear patterns, such as traffic patterns. And there are many results in the literature showing that. So the question is, why don't we see them deployed much in real networks? One of the reasons is that most neural networks have been done on supervised learning, which means they are training the models to detect and classify non-malicious traffic patterns. So you need to collect many packets from every attack and label it as being malicious or normal. And when a new attack comes, you need to retrain the model from the start. This usually means very strong GPU servers that can't be deployed on small switches in the field. Such AI tasks consume very high compute resources that if you run them on a standard CPU, a model with 15 layers, with 100 input features, it will be able to handle about 500 packets per second. Prior work was done on unsupervised learning solutions that brought several advantages. There is no need to label the data, so you just train on normal data. Thus, the training phase is much easier. For a new solution based on Ensemble or group of small neural networks called Autoencoders that have shown to be lightweight, thus achieving much higher performance. And being lightweight, these solutions can be deployed online for both the training and the inference phase. They are done on a per packet basis without storing huge amount of data, as they are only keeping incremental statistics. Such recent solutions are able to handle only about tens of thousands of packets per second, which is a great improvement, but still far from being able to handle millions of packets per second, as can be seen in modern networks. One of the recent works that achieves those 10,000s of packets per second is called KitNet. It's a work, and the work that we will be presenting today is an enhancement of this work. The KitNet work was performed by a team from Ben-Gurion University, Yisroel Mirsky, Tomer Deutschman, Yuval Elovici, and Asaf Shabtai. In a classical framework of anomaly detection system, you have packets arriving from the network to a server or an AI server. It takes a look at the sequence of packets it receives. It then runs some anomaly detection algorithm and places the results in the log showing the anomalies it detected. If we look at what the AI server is actually doing, it needs to capture the packet, parse the packet headers, extract basic features from the stream of packets, such as packet header, packet size, arrival time of the packets. It then creates some advanced features like calculating mean and standard deviation on the recent history of the streams. This is called damped incremental statistics, and then runs the anomaly detection algorithm. Now, in our work, we have created a new feature extractor that classifies the incoming packets into 5 tuple flows, or what's called TCP-UDP connections, and then create statistics on a large group of such packets, instead of looking at the size and the arrival time of each and every packet. For example, we counted the number of packets in each size range and keep these counters called histograms in a small database. We then created an event that includes these smart statistics and pass them for additional feature extraction that creates damped incremental statistics and for the anomaly detection, but this time on a reduced amount of events. We haven't changed the feature mapper and the ensemble of autoencoders. We only adapted the number of neurons to fit the new smart statistics. But as it now works on a lower events per second rate, the overall performance is dramatically improved. For those not familiar with autoencoders, it is a type of artificial neural network that creates in an unsupervised manner a small representation of the dataset. It was initially created for dimensionality reduction of images while ignoring noise. And the way it works is on the encode phase, you reduce or compress the data, and on the decode phase, you reconstruct the image. And using iterations, you attempt to have the reconstructed image to be as close as possible to the original input. During these iterations, you update all the coefficients of the neurons, and the delta between the reconstructed output and the input is measured in mean square error. Now, this same concept is now being used for anomaly detection. Instead of images, you can train the model on normal traffic and teach it to identify the most important, common, reduced characteristics of this normal traffic. And on the inference step, when the input to the model is anomalies, but the model itself is trained for normal data, the reconstructed data you receive is totally different from the input. Thus, the delta between the output and the input is huge. but make it easy to notice and declare that this is not normal inputs. With an ensemble of autoencoders, you're able to improve performance by first having a phase in which you are batching or mapping the features to several smaller autoencoders. Such a model consumes much lower compute resources compared to having one huge multi-layer neural network. If it consumes less compute resources, then for the same compute power, you can achieve much higher packets per second performance. If we look at the updated framework, after we added the smart statistics for an aggregate of packets and thus reduced the events per second, we can notice the following. The packet capture, the packet parsing, and even flow classification are all functions performed by any networking device. Modern switches can also provide the smart statistics as part of their programmable pipeline. All these functions need to be performed on a per packet basis, on very high packets per second, thus best suited to be performed by switching devices. The smart statistics on a much lower events per second can now be streamed to a CPU for the feature extraction, incremental statistics, covariance, multiple decay factors, and to the ensemble of autoencoders, the neural network itself. And this can be performed by a centralized CPU, or better yet, by an AI engine. This step by itself allows reaching very high performance. Going even further, embedding the CPU and the AI engine inside the switch will allow distributing the anomaly detector, achieving even higher performance, and also reducing the reaction time from detecting anomalies to enforcing the change in the switch itself, for example, blocking the malicious attack. We have tested our algorithm on a live traffic we created in our lab. We are targeting a use case and scenarios that involve IoT devices and other sensors, such as surveillance cameras. We checked that we can identify anomalies in the behavior of the sensors. We started by training the model on normal traffic over a few minutes of traffic. This is something that can be done offline, but also on a live network that you know is currently running normal traffic. Then on the inference phase, when we put the AI model in action, we injected both normal traffic, showing that the system didn't provide any false alarms, and also injected anomalies, showing that we were able to identify those. The anomalies were, for example, changing the setup of the camera in terms of resolution and image quality. This could mean someone have maliciously or mistakenly changed something in the camera. We also tried attacking the sensor by sending traffic to it, traffic that was not part of the normal traffic. This could indicate someone is trying to log in or attack the sensor. And the last anomaly, we also consumed more traffic from the camera by adding additional targets. This can mean that an unauthorized user is getting the video stream, and we were able to identify this too. So if we look at the results, we see that they were extremely good. When we injected normal traffic, the mean square error was below the threshold. Thus, we classified the traffic as being normal. But when we added anomalies to the network, we were able to identify them easily. One should notice that the number of events, each dot in the graph is an event, is much lower than the number of packets in the network. This is due to the advanced feature extractor that we created, that created only several events per second. In the segment we call Anomaly 2, we first started with normal traffic, and only after a few seconds, we started sending traffic towards the sensor and identified that. In terms of numeric results, for the training phase, we see that very quickly the algorithm is able to create the neural network model with all the coefficients. and reach a very low mean square error. And on the inference phase, we reached more than 2 million packets per second when the advanced statistics are created by the switch itself. Remember that we started with 500 packets per second with supervised learning, and that the previous kit network achieved tens of thousands of packets per second, and now we can achieve 2 million. And if we look at the ratio of time the CPU was spending doing feature extraction versus the time the CPU was performing the neural network itself, we are currently using a regular CPU for that, not a dedicated AI hardware chip. We can see that 97% of the time is spent on the neural network, which means that if this task will be moved to a dedicated hardware, performance is expected to be dramatically improved to tens of millions of packets per second. As for the scores, the metrics, we checked accuracy. This is a proportion of the number of correct classification from all classification. Precision, checking if there is any false positive. Recall, checking if any false negative. And an F1 score, which is a balance between precision and recall. Best score metrics is 1. When we look at the per event score, the scores are good, despite the aggregated nature of the solution. Note that at the same time, we have multiple events. Some are normal and some are abnormal. And it was not always clear to define what the correct classification of events. But receiving a precision score of 1 was very important to us, as it means no false positive, i.e. no false alarms. When we defined a full second as being abnormal, if it had at least some abnormal events, then the scores we receive are actually perfect. We need to acknowledge that we have tested this algorithm on a stable use case of sensor behavior. And in a more dynamic environment, results may not be as good. So to summarize, neural networks can be used for classification and for anomaly detection using unsupervised learning, now also for packet networks. A key challenge in applying AI for packet networks is performance, when the AI events per second is the same as the number of packets per second, which can be a huge number even in a small access switch. Modern switches are now providing very smart statistics and telemetry capability that allow providing information on a group of packets of each flow. This allows having the AI machine receive and deal with aggregated events instead of on a by-packet basis. In this work, we have shown that accurate anomaly detection is possible with very good scores and for high-speed networks. Thank you very much.